Hello and welcome. This is the experimenter, and today we will be taking a crazy integral which is there on the screen. You can see the highlighted portion of the screen, and I would strongly suggest you to pause this video right here and just go and try it out yourself, because you might just come up with some interesting solution. So let me just restate the integral. It goes on something from 0 to 1, and the function is the product of x and the nested sequence of cosines followed by a dx. But before I start digging into this, let me just analyze the graph of the function in GeoGebra. So here we are. So first I'll plot the graph of x times of cosine x. This is the graph. As you can see, the graph is pretty much oscillatory, and that is quite predicted, as we know cos is an oscillatory function. So from the next graph onwards, I'll be increasing a cosine term in the nest. So the next graph is of the function x times cosine of cosine x, and I'll be adding one notation just because this is too much tiring to repeat cosine so many times. So I will just mention the number, and by that number you will just understand that how many times the cosine is repeated. For example, this graph I will say 1. That means it is the graph of x times cosine x. So for this graph, the one in the yellow, this is the graph of x times cosine of cosine x. So instead of saying that, I will just say 2, and so on. So this is 3. Cos is repeated thrice. This graph has cos repeated 4 times. This one has cos repeated 5 times. In this graph, cos is repeated 6 times. In this graph, cos is repeated 7 times. And finally, I'm just skipping this for a certain approximation. In this final one, the one that is shown in yellow, cos is repeated 78 times. So there is one thing we can actually predict from this presentation, that the function is getting more and more linear, and it is resembling a straight line. I think from the graph it is clear that with the increase in the number of cos, the graph is getting linearized and the function is becoming more and more like x. But the slope of that function is not yet determined. But now let us just carry on the normal procedure and see what does it reveal. So here we see that this infinite nested sequence of cosines is the craziest part of this integral, as the title suggests, crazy integrals. And this is my way of attack. Put cos of cos of cos, that is the infinite nested sequence of cosines, equals to some arbitrary number or variable. Number is not a good word here, and let's just put it t. Now it's time for observation. If you just look at the thing, the cos of something, the inner part is also an infinite nested sequence. So we can just put that also equal to t. So the function, I'm just repeating this once. You can see that there is the infinite sequence of cos of cos of cos. Since this is infinite, if we just take one cos out, the rest of the sequence will still be infinite. So we can just put that equals to t. So the entire equation reduces to cos t equals to t. And again, we'll have to carry on some graphical procedures. So after putting cos t equals to t in the graph, we can see the value of t that is close to this is something around 0.7391. Of course, that depends on the precision, but for this purpose, let me just take up to 4 decimal places. And now the interesting part, as we can see, the whole infinite sequence of cosines, whole infinite nested sequence of cosines now gets reduced to this constant, which is 0.7391. This thing was suggested by the graph graphical methods we have just used in the beginning of this video, where we analyzed by increasing the number of cosines in the nest. And as we saw, as we increase the number of cosines, the graph is getting linearized. But the slope was not determined there. I mean, it could be determined from graph, but we didn't. So generally by algebraic method, we found out that the value of t is 0.7391 from the graph. So this whole integral reduces to a very basic form, which is just x into 0.7391 into dx, and just carrying on the integration like usual. By usual procedures, we get 0.7391 by 2 after putting the limits, which is equal to 0.3695, and that's the answer.